Welcome to AI Paper Podcasts. We've got a fascinating paper today diving into a challenge with multimodal AI, models that see images and get text.
Right.
But the problem seems to be they still kind of default to thinking in words, even when they're looking right at a picture.
Exactly. And that's the core issue this paper tackles. Even really capable multimodal large language models, MLLMs, they see the image, sure, but the reasoning, that often happens via text. It's like describing how to get through a maze instead of just, looking at the path.
Which creates this modality gap, as they call it, hurts performance on visual stuff.
Precisely. So the paper introduces this idea. What if the AI could plan directly using images, thinking visually step by step?
Visual planning.
Yeah, and they propose a method, VPRL visual planning, via reinforcement. Learning to train models to do just that, generating image sequences representing the plan. No text needed for the planning itself.
And the key takeaway, does it work?
It seems so. The results show this visual-only approach, especially with the RL boost, significantly beats the traditional text-based methods on these visual planning tasks.
Wow. Okay, so the implication is potentially AI that can navigate or manipulate objects more intuitively, almost like how we might visualize steps.
That's the exciting prospect, yeah. Moving beyond just describing the world to actually reasoning within its visual structure.
Okay, let's unpack this properly then. We've got this work focusing on getting AI beyond just text descriptions for visual tasks.
Right. And it highlights that even with MLLMs that do process visual input, their core reasoning engine is often still language-based. Like you said, they translate the visual problem into a language problem first.
It's like having eyes but choosing to navigate by listening to directions only.
That's a great analogy. And this translation, this modality gap, it causes problems. It loses crucial details.
So where does this gap really show up? What kinds of tasks make it obvious?
Well, the paper points to tasks that are really vision first. Things like visual spatial reasoning, navigating complex spaces like mazes, even predicting how objects might move.
Stuff where a picture is worth 1,000 words, but the words aren't quite precise enough.
Exactly. Text can be ambiguous, especially about spatial stuff, like slightly to the left. What does that mean visually? Benchmarks they reference confirm that purely language-based reasoning just doesn't cut it for these.
Okay, so here's the really cool part then. This visual planning idea. What does it actually look like?
It means the planning happens entirely in the visual domain. So you give the model an initial image, say where the agent is now.
Okay.
Instead of outputting text like move up, it generates the image of the agent after moving up, then the image after the next step, and so on. It builds a visual sequence, a kind of mental movie of the plan.
Ah, I see. So the output is the plan, just shown visually.
Precisely. Figure 1 in their paper shows this really clearly. You see the visual steps versus like a long text description from other models.
That's fascinating. But how do you actually train a model to do that effectively, to generate a good visual plan?
Yeah, that's the challenge. They introduced this two-stage framework they call VPRL, Visual Planning via Reinforcement Learning.
Okay, 2 stages. What's the first one?
Stage 1 is policy initialization. The key here isn't perfect planning right away. It's more about getting the model to generate valid visual steps and, crucially, to explore the possibilities.
How do they do that? Supervised learning?
Yep, supervised learning. But here's the interesting bit. They train it on random trajectories within the environment.
Random, not optimal ones. Wouldn't that be better?
You'd think so, right. But they actually compared this. They have a version called VPFT Visual Planning via Fine-Tuning, where they only trained on optimal paths using supervised learning. And it learned those optimal paths well, but it got brittle. If it took one slightly wrong step, it didn't know how to recover or explore alternatives. It hadn't seen enough messy situations. Figure 6 compares them, showing VPFT gets stuck, lower entropy, higher invalid moves initially.
Ah, so the randomness in stage 1 is for robustness, for learning how to handle things when they aren't perfect.
Exactly. It helps the VPRL model explore the whole space of possibilities, which turns out to be vital for learning effective planning later on.
Got it. So stage 1 is about exploring and learning valid moves. What's stage 2 then?
Stage 2 is the RL optimization. This is where the actual planning smarts get honed. They use reinforcement learning, specifically something called Group Relative Policy Optimization, or GRPO.
Okay, RL. So the model tries generating visual plans and gets feedback.
Yep. It generates sequences of visual states representing its plan. Then it needs to figure out if those steps were good.
How does he get that feedback? Rewards for images. That sounds tricky.
It is clever. They need to interpret the action implied by the change between one generated image and the next. They use a rule-based function for this in their environments, mapping image pairs to actions like move up or pick up object.
Okay, so they translate the visual transition back to an action label.
Right. And then they use a pre-computed progress map. Think of it like a map showing the shortest path distance from every point in the environment to the goal.
Ah, okay. So they can see if the predicted next state is actually closer to the goal.
Precisely. Based on where the predicted state lands on this progress map, the implied action gets categorized. Optimal if it makes progress, not optimal if it doesn't really help or slightly hinders, but is still valid, or invalid if it breaks the rules.
Invalid like walking through a wall.
Exactly. Or the agent disappearing or making a contradictory move, stuff that just can't happen in that world.
And the rewards follow these categories.
Yep. Simple but effective. Positive reward, like +1 for optimal. 0 reward for non-optimal. But a big penalty, like -5 for invalid actions.
So it really learns to avoid mistakes, like hitting walls.
Exactly. It learns the environment's constraints visually. Figure 3 actually shows examples of these different trace types, optimal, non-optimal, and those invalid ones it learns to avoid.
Okay, so that's VPRL. How did it actually perform when they tested it against other methods?
They ran comparisons against several baselines. There was VPFT, the visual supervised only version we talked about.
Right, the one trained only on optimal paths.
Then they included standard textual baselines, just fine-tuning a model on text sequences of actions. And importantly, they also tested powerful, state-of-the-art MLLMs using inference-only methods.
Like asking them directly or using chain of thought? Which models?
Yeah, direct answer and chain of thought. They used both open source models, like Quinn 2.5 VL Instruct, and top closed source ones, Gemini 2.0 Flash and Gemini 2.5 Pro.
And they made sure the model sizes were comparable.
Yes, they focused on comparing models around the 3 billion parameter mark, like the LVM vision model they used for VPRL and VPFT, and the Quinn model.
So the big question, how did VPRL do?
The results look pretty strong. VPRL significantly outperformed all the baselines across their test environments.
All of them, including the big Gemini models.
Yes. On tasks like Frozen Lake, Maze, and Mini Behavior, which involved picking up and dropping things, VPRL had much higher success rates.
Yeah.
They measured things like exact match, did it solve it perfectly, and progress rate, how much closer did it get?
And the numbers showed a clear win for VPRL.
Yeah, substantial gains, often over 20% improvements compared to both the textual methods and even the visual VPFT baseline. The tables and figures in the paper lay this out quite clearly.
Wow. So it really seems like thinking visually is the better strategy for these kinds of problems.
The evidence here strongly suggests that yes, especially as tasks get harder. Figures 5 and 8 show this really well. The performance of textual methods, even sophisticated ones with chain of thought like Gemini, it just drops off a cliff when the maze gets bigger or the task gets more complex.
But the visual planners held up better.
Much better. VPRL and even VPFT to some extent were more robust to that increase in complexity. And remember those invalid actions.
Like walking through walls.
Yeah. Table 5 shows VPRL learned to make far fewer of those invalid moves compared to VPFT. That RL penalty really worked. Figure 4 has a nice comparison on Frozen Lake, where you see text methods failing while VPRL finds the path, likely because it has a better grasp of the spatial layout.
So it's not just getting the right answer more often, it's actually learning the rules of the environment better through that visual feedback loop.
Seems that way. It's understanding constraints visually, not just trying to follow potentially ambiguous text instructions.
What about generalization? Did they test if it could handle new environments it hadn't trained on?
They did. They tested on out-of-distribution or ODE environments, basically mazes or grids that were larger than anything seen during training.
And how did that go? Usually performance drops there.
Performance did drop for all methods, which you'd expect. But VPRL still maintained a significant edge over VPFT and especially over the textual models. Table 7 and Figure 9 show these ODE results.
So it suggests VPRL wasn't just memorizing training layouts.
Right. It seems to have captured more fundamental visual planning strategies that could transfer, at least to some extent, to new, unseen situations.
That makes a lot of intuitive sense. Visual patterns for movement might be more generalizable than specific sequences of left, right, up.
Yeah, the underlying spatial logic might transfer better visually.
Okay, this is really promising stuff. What did the paper mention as limitations or where this could go next?
They pointed out a few things. One is model size. They used a 3 billion parameter vision model because that's what was readily available. Applying this VPRL approach to much larger, more capable vision models or native multimodal models could be really interesting.
Scaling it up Makes sense.
Another point is computational cost. Generating sequences of images during inference takes more compute than generating text. So future work might look into finding more compact or efficient visual representations for planning. Maybe not full images every step.
Right, optimizing the visual thought process.
And the last main one was the state-to-action mapping. Their current system uses handcrafted rules to interpret the visual changes, which works for their grid worlds, but might not scale easily to complex real-world scenes.
Yeah, you can't predefine rules for everything out there.
Exactly. So they suggest maybe using more advanced computer vision techniques like object segmentation or contour detection to make that action parsing more robust and generalizable to less structured environments.
Okay. So wrapping up, we've taken a deep dive into this fascinating idea of AI planning directly in images, skipping the text translation step.
Yeah, and the key takeaway seems to be that for these inherently visual spatial tasks, embracing this visual thinking, especially supercharged with reinforcement learning, unlocks some serious performance gains and makes the models more robust.
It's almost like giving the AI a visual imagination to plan with.
It really is.
Yeah.
And it resonates with ideas from cognitive science like dual coding theory. The idea that humans use both verbal and nonverbal, like visual channels, to process information. This suggests AI might also need strong, distinct reasoning pathways for different modalities.
It definitely raises the question, as AI gets more multimodal, how crucial will it be for them to develop these modality-specific reasoning skills instead of just forcing everything through, say, the language pathway?
Well, this paper certainly gives us compelling evidence that for visual tasks, thinking visually is a powerful strategy. It pushes us towards AI agents that can maybe interact with the physical world more naturally.
So here's a final thought to leave folks with. If AI can learn navigation and manipulation by seeing and imagining the next visual step, what other complex tasks could this unlock?
Right, think about things humans do visually. Designing a building, maybe performing surgery guided by imaging, even artistic creation or complex assembly tasks.
Things where visualizing the sequence of spatial relationships is absolutely key. Could pure visual reasoning be the breakthrough needed there?
It's a really interesting possibility to consider. Where else could thinking in images take AI?